Our last speaker is Andrea Fontanella, who is going to tell us about a new non-relativistic.
So, first of all, hi everybody, and thanks to the organizer, I don't know if they are here, for this nice conference and for the opportunity to speak, of course. So, I will talk about a new non-relativistic holography, which is based on those results. So, this is a later version of this longer paper done in collaboration with Juan Miguel. And this letter, you will see it appearing in PRL. And the second part of the talk, which will be about a quantitative test of this new non-relativistic holography, will be based on this other paper done with Marius Deleuve and also, of course, Juan Miguel Nieto. So let me first give you a bit of motivation, why to bother about it. So, why to bother about non-relativistic holography? Well, first of all, it is a natural example of non-ADS and also non-Lorentzian. So for these reasons, they are naturally, they have two ingredients that they go away from the ADS usual case. First, another reason is that it is timely to study non-relativistic holography because it goes along with the current effort of exploring how general holography is, like the flat space program. And also you can wonder about some conceptual questions, such as, is non-relativistic holography working as in the relativistic case? And if it does not, in what does it differ? And then if you understand the differences that it has from the usual relativistic case, this might help you to understand how holography behaves at the universal level, perhaps. Apart of those more philosophical, perhaps, questions, there is a more concrete one. It is non-relativistic holography a simplified setting where you can test holography? And we will see in this talk, indeed, it seems like that's the case. So in this talk I will discuss the first example of non-relativistic ADS5 CFT4 holography, which has a relativistic worksheet, as I will comment later, proposed on this paper. And I will talk about a possible quantitative test that you can make to support this claim. So, first let me give you a bit of introduction about the non-relativistic limits in string theory and in gauge theories. So, in string theory, this was first proposed by Gomis-Oguri in the flat spacetime, later generalized in ADS5 cross S5 by Gomis-Kamimura, often I will refer as GGK. This limit requires that you turn on a closed B field that is critical to cancel a divergence. And the features that it has at this string theory is that the target space geometry becomes non-relativistic. It is a string Newton-Cartan geometry, but the worksheet of the string remains relativistic. And it is because of this relativistic worksheet that you can still compute a beta function and show that it vanishes, and therefore this model is anomaly-free. So I think this is a quite attractive feature. And this is a cartoon of what is happening. You have your string in the relativistic setting, and after taking this Gomis-Oguri type of non-relativistic limit, you have that your space-time becomes described by two degenerate metric tensors. One is called the longitudinal, tau, and one that is transverse, called E. So let me move what happens to non-relativistic limits in gauge theories. Well, also here it has applied to a plethora of them. Let me mention some relevant works, like for a Maxwell theory plus a scalar field relativistic, you can take a non-relativistic limit and get a so-called Galilean electrodynamics. You can also apply that to Supernian Mills and get a Galilean version of it, and you can do also much more cases, and I will refer you to the review of Stefano. At this point, you can actually quite naturally ask, are all those non-relativistic string theories and gauge theories related by some holography? And if yes, how does it happen? So as Jelle mentioned, and also Stefano in their talk, there is some conjecture when the worksheet is Galilean. But in this talk, I will not consider Galilean worksheet. The worksheet will be relativistic. So it is the Gomis-Oguri action that we discussed here, which has a vanishing beta functions. So let me move about telling you what we did. So our approach is quite simple. So basically we take the Maldacena setting of ADS5 CFT4 correspondence, which is this line, and we ask what does it happen if you take the non-relativistic limit on all these boxes, basically? So if you apply a non-relativistic limit at the string in ADS5 cross S5, you go down to the GGK limit, the one of Gomis-Oguri type of string theory. But the question is, what does it happen? What is the other limit that you need to take on the other boxes of this duality? So what we did in our work is to answer those question marks, and we had this more coherent picture. So upstairs is the relativistic Maldacena duality. On the bottom line is what you get after taking the non-relativistic limit. So you have that the stack of these 3 branes becomes a non-relativistic stack of different branes, which they still emit a notion of the coupling limit, a near-horizon limit, and this near-horizon limit precisely leads you to the string Newton-Cartan ADS5 cross S5, where we have our Gomis-Oguri string. What happens on the other side? So here you have the DBI. The DBI becomes a non-relativistic version of it, which is based on this Newton-Cartan Minkowski space. Here again you can take a low energy limit, and this we will see later on a little bit of details. It leads you to this Galilean electrodynamics with 5 scalar fields in 3+1. And so after filling these boxes, it's quite natural to say, well, those ones should be the new duality that we want to propose. And so that's what we did, and we supported this new duality by computing matching symmetries. So we computed the killing vectors on the string theory side, and we evaluated them on the boundary, and we show that they precisely match the on-shell symmetries of this GED, which was computed previously in the past, also when you supplement it with the 5 scalars.
Is there any supersymmetry in the Galilean electrodynamics?
I'm doing only bosonically here. Yeah.
What do you mean by on-shell symmetry?
On-shell symmetry means the symmetries of the equation of motion of this GED. So there is a... Sorry.
I guess I could have guessed that. But are those, is that legit? I mean, does that include, for example, things that aren't necessarily symmetries of the action and don't necessarily occur?
Yeah, I can comment later maybe about that, but so the idea is that how can you extend the off-shell? That's a good question, and I think it's not been answered, but this is also the only work where they did appear. There was no other further work where it has been studied how to extend the on-shell, off-shell. So yeah, that's definitely a good question, and I want to talk. We can comment maybe at the end of the talk about that. So what I want to say is that there is a Penrose here boundary realization. So you can take the Penrose boundary of this geometry and show that this is precisely the 3+1 Minkowski space where your GD is living. So there is also a Penrose realization of this duality. Let me give you a bit of details. There will be only this slide, I promise. So on the string theory side, your stack of different branes retains the notion of horizon, as I mentioned before. And this is very useful that it retains the horizon, because then you can still apply the Maldacena argument, where you decouple your string theory from a near horizon region and something that is at infinity, and that is very important in this construction. And also what we did was to consider the Gomis-Kamimura limit of the string theory. But there are more, and I will mention more later. But this specific Gomis-Kamimura gives you a longitudinal metric that describes ADS2, and something transverse that is basically a flat Euclidean space with some warp factor. So the reason why we took this limit is just because it was already worked out in the past, and it was natural to start with, for us, it was natural to start with that. And then you can wonder what happens on the gauge theory side. So what is the analog of this GGK limit on the DBI? So it should correspond, it is quite natural to guess that it should be a stringy non-relativistic limit acting on your Minkowski's coordinates. And here, to do that, you have 2 possible ways to do it. One is that you take your Minkowski coordinates, time and space, and you rescale them by C, and you leave the other transverse invariant. Or you can also equivalently do the other way around. You can rescale by 1/C the transverse one and leave time and x1 invariant. At this point, those two point of views seems very equivalent. And then you take C to infinity. However, these two different ways of rescaling, they leads you at the end, after taking the decoupling limit of your dBi, to two very different theories. One is this Galilean super-Yang-Mills string theory plus 1, which retains a notion of gauge, a non-abelian gauge group. It is still UN, and it is also an interacting theory. On the other side, the second option leads you to n squared copies of this Galilean electrodynamics, which is a U1 gauge theory, and at the moment it seems like it is a non-interacting theory. So option 2 also, let me say that it also requires that you rescale your gauge fields by overall rescaling of 1 over C. And this is precisely the reason why you are abelianizing your gauge group. It is because you have to do this sort of rescaling in order to have a consistent limit, so to not have divergences. And so in this way, it resembles a bit like a weak coupling limit in a sense. So,
quick question.
Yeah.
On the Kimura side, there you include, say, on the closing side, you include a critical B field.
Oh yeah. You
do the same on the DBI side?
Precisely. And that is the B field that you put on the DBI, it cancels a critical divergence. Yes, it's important. Yeah. So option 1 at the end. So you have those two theories at this point, and how do you discriminate them? So at this point, the way that we discriminate is because option 2 is the only one that realizes the string theory, the string symmetries that we computed from the string side, and option 1 does not. So that's why we choose the second option at the end for our holography description. Let me say that this picture, you can generalize it. So non-relativistic limits are not unique. There are many. We took the Gomis-Kamimura as an obvious starting point, I think. Has been generalized to other non-relativistic limits by Lambert and Smith, and they also, the same authors, applied the same ideas to the M2 branes in M theory. You can ask what are other limits. Can you repeat like this construction, for instance, for the Carroll limit? And we are doing something on that. Or you can also wonder, can you take the same limits of the DSFT from the point of view of the flat space limit instead of Carroll or non-relativistic? In principle, you could. It is a bit more complicated because the D-free brane metric now loses the notion of horizon. So it's not clear how the Maldacena argument will be incorporated really into this limit. Finally, okay, I arrived now to the quantitative test. So there is a famous test of ADS-TFT, which is the string spectrum needs to match the scaling dimension of gauge invariant operators. So this program has been done very successfully in the relativistic ADS-TFT, and integrability was the crucial ingredient that you needed to solve such a problem. So the question is, can you repeat such a test now in the non-relativistic theory? First of all, you can wonder, is non-relativistic string theory integrable? Well, so we have done some work to construct a Lux pair for this GGK theory. Then we also looked at what is the spectral curve associated with the Lux pair, and we found the surprising result that the spectral curve trivializes. And the reasoning is because the isometry group becomes a non-semi-simple algebra after taking the non-relativistic limit. And most of the reasoning is in this statement, basically. But however, so this is because, so here this is a program that you would like to attack with integrability. However, I want to tell you that recently we were able to solve this spectrum problem, now without integrability, just with a heavy perturbative analysis. So the perturbative analysis, basically we took the action and just perturbatively expand around a vacuum. The vacuum cannot be the BMN one because, as we showed previously in a previous paper, the BMN vacuum does not survive the non-relativistic limit. If you want, it's not a solution for your non-relativistic action. Instead, the simplest vacuum that survives the non-relativistic limit is a folded version of this BMN string. So it is not a point-like anymore, but it is an infinitely extended string. And this is a vacuum that is suitable with your light cone gauge quantization. So we took this vacuum, and then we did very complicated field redefinitions, and we expanded perturbatively in the string coupling. And we show that we went up to the sixth sestic term in the fields, and we show that all the corrections vanish, and you remain just with a quadratic action, which describes free, massive, and massless fields in ADS2. And then for this action, you know what is the spectrum. It's in terms of Gegenbayer polynomials, and so you know what is the spectrum now. So we have quite a strong confidence saying that this spectrum might hold at the non-perturbative level just because we went up to the sextic term in the field. However, it's still an open problem to show it that there is a non-perturbative transformation that leads you the non-relativistic action to these free, massive, and massless fields. Okay, so let me summarize and say what are the future directions. The summary is that we have a new approach to construct a non-relativistic ADS5 CFT4 correspondence, and this new approach leads us to propose a new duality. It's a very concrete duality between two theories. One is the Gomi-Soguri string theory in this funny geometry. It's a new string Newton-Cartan ADS5 cross S5. And on the gauge theory, you have these n square copies of the Galilean electrodynamics. So now that we propose this duality, is for the future direction, the natural question of the following. Make some quantitative test, such as compute the scaling dimension for this gauge theory, and check that they do match the string spectrum, so the spectrum of free fields in ADS2. You can also wonder if there are other quantitative tests. Indeed, there are you could make like a confinement or Hagedorn transition check between the gauge and string theory. And you can also repeat this when you have some temperature, which requires us to have some non-relativistic stringy black hole, which we have some hints that they might do exist, because as we showed, the non-relativistic D3 brane retains a notion of horizon. So you might have black holes with a non-relativistic stringy behavior. And finally, what about generalizing this construction to other limits, like the Carroll or new non-relativistic limits, or even more? Okay, so that's it. But before closing, let me give an announcement. So we are organizing next year a workshop called Non-Lorentzian Geometries and Their Application, together with Eric. The workshop will be at Trinity College, Dublin. As a preliminary dates, you may save in your diary that those are the dates. Those are the topics, basically non-relativistic strings and theory holography, Carroll-related phenomena, and mathematics of non-Lorentzian geometries. You will hear from us with some announcement, more precise announcement in the future. So stay tuned, and hope to see you in Dublin.
Maybe you mentioned it, but I missed about the other option, option one, it had supersymmetry.
No, so
In the limit?
you can complete actually with supersymmetry, and I think Neil is what also is addressing this question of adding supersymmetry. In our work, we just did everything bosonic.
No, I mean, you have these two options, two ways to scale.
Yeah.
The limit.
Yeah. This one.
Superangles, I'm assuming you have.
Oh yeah. Here you mean I should drop the S? You mean?
No, I'm asking if the S is there or not.
I'm doing the bosonic, so it's a bona fide thing. Yes. So you need to prove that you can add supersymmetry. I haven't done it.
Okay.
You did it, right?
No, we've only actually shown so we claim that there's an S dual to that.
I see. Okay.
That we did show.
Okay.
But I would bet that it's.
I would bet yes. Yeah. I think it will work. You just have to make your hand more dirty with fermions. Yes, it is possible. There are no obstructions. Yes.
Yeah. One final question for Andrea.
Yeah, it's also a little bit about option 1 versus 2. Because option 2 is helium theory, right?
Yes.
Isn't that slightly off? Like, Let's put it like this, why does the non-relativistic limit abelian nice
Yeah.
the non-abelian version?
Well, so the reasoning is because you are rescaling your one-form potential by 1 over c. That's what we are taking as a non-relativistic limit in option 2, together with this coordinate rescaling. So when you take this a with 1 over c a, all your covariant derivatives that they have a partial a plus commutator of a or something like that, all those terms that they have, like they become subliving in the power 1 over c, because the commutators are higher order in the one-form potential. And that's because since you have higher order terms, so basically all your non-abelian structure is in the higher order terms of your one-form potential. And then you take c to infinity and they suppressed, basically. So it is because of this supplemental limit that you take.
So if you had stuff that was, say, in the fundamental representation of the adjoint, or something like that, you could rescale the charge to keep the interacting terms?
And there, if you could repeat the question, because I might have what you said.
Okay. So you mean?
Well, just imagine, suppose I did real electrodynamics with the adjoint field, so the charge field.
So you mean that you are at the relativistic level, you are in the super Young Mills, or you are already, you mean that you already took a limit and.
Well, yeah, you're thinking further than I was. I was just thinking, you have a 1 over c in your coupling, and hence that's killing all the interaction terms.
Yes,
The
yes.
interaction, and that's because everything's just commutative. But suppose I had something in the fundamental or something just electrodynamic, so that actually had electric charge Q over C times.
I see what you mean. So basically you reabsorb by redefining a charge such that you, that's interesting. Yeah, could be, yeah.
I think a related question would be whether you could rescale the Yang-Mills coupling.
Yeah.
Yeah, because that's a G.
Yeah.
Okay.
Yeah.